Okay, good afternoon. So welcome to ESS 495 Rocks and Stars Seminar. Hopefully you all got a copy of the handout that was being distributed as you came in. That is essentially a syllabus for the class, giving the tentative speaker list. It is possible that will change. For those of you viewing online, it's just a copy of the website that you went to log into viewing online. And then on the second page of the handout is the questions for today. So the format is that every speaker during the course of their talk will answer 3 to 4 questions. You're responsible for being able to note the answers for those questions. On the last day of class, so that's the last Thursday of class, not during finals week, this is during the last week, there will be a quiz that you will take in order to get credit for this class. The questions on the quiz will be a subset of those that the speakers have answered during their talks during the course of the quarter. Today is the only day that you will get a handout with those questions. They are on the last sheet of the handout. For those of you viewing online, you can just click the link of the speaker's talk and be able to see the questions. From next week on, you will be responsible for bringing those questions in yourselves. You will not receive a handout. The questions are typically posted on the Wednesday afternoon right before the following day's seminar. So if it's Tuesday and you're looking for the questions and they're not posted yet, just give me a day. I probably haven't gotten them from the speaker yet. So just as I sort of mentioning that to get credit for this class, you have to pass the exam that is on the last day of class. So with that, I will then switch over to introducing our speaker. So our speaker today is Rob Hoyt, Dr. Rob Hoyt. He is the CEO and Chief Scientist at Tethers Unlimited, a local aerospace company here in this greater Seattle area. And you're in Bothell? Yep. Yeah, so up in Bothell. I went over and visited them when they used to be in Linwood, at your early one, a long time ago in Linwood. Rob previously worked at Science Ops Incorporated, and also right after getting his PhD, he worked as a scientist at the Los Alamos Research Laboratory. He got his PhD here in University of Washington in aerospace engineering, and got his Bachelor of Arts in Physics from Williams College. So with that, I'll turn it over to Rob.
Thanks. Alrighty, so what I'd like to talk to you about today is work that we have been doing at Tethers Unlimited over the past almost 19 years now, working to develop technology called space tethers for a variety of different applications. So what I'm going to talk about today is, first I'd like to start out by giving you a little bit of background on my company, talk about some of the other stuff we do as well, and then get into what is a space tether, and then how can you use them. I'll talk about some of the prior space flight experiments that have been flown using various kinds of tether technologies, talk about the underlying physics behind how space tethers work, and then I'll talk about a couple different specific applications. One is called electrodynamic propulsion, the other is called momentum exchange propulsion. And both of those are ways that you can use the space environment to provide propulsion to a spacecraft without burning up fuel. So it's potentially a way for greatly reducing the cost of many space missions. So to give you a little bit of background, as Eric said, I'm the CEO of Tethers Unlimited. We're a small aerospace R&D company located right across the highway from the UW Bothell campus. We got started back in 1994 when I was a grad student here at the University of Washington, and I started working with a fairly well-known and experienced older engineer called Bob Forward, who some of you may have known from his science fiction writing. And we got started mainly through NASA's Small Business Innovation Research Program. It's a program where NASA gives grants and contracts to small businesses to help them develop new innovative technologies. For the first 10 or so years of our existence, we were very focused on this space tether technology that I'll be talking about today, and we still do a lot of work on space tethers. But since then, we've branched out quite a bit into a number of other related space technology areas, including robotics. We're doing robotic arms for very small spacecraft, a variety of different radio communication systems for very tiny spacecraft, and we have a growing technology development effort where we're applying things like technologies like 3D printing and other additive manufacturing processes to enable us to fabricate spacecraft components both here on the ground and up in space. But what I'm going to be talking about today is kind of our core efforts on space tethers. So what is a space tether? A space tether is basically a long, thin cable or wire deployed from a spacecraft. And that cable or wire can be anywhere from a few meters to hundreds of kilometers long. And there are a couple different ways you can use them to use tethers and the space environment to provide propulsion to a spacecraft. The first one is one where if the tether is high strength, is basically a strong rope, you can use it as a sling to enable one spacecraft to transfer orbital energy and orbital momentum to another spacecraft. So like a big space station could use a long cable to sling a smaller spacecraft from a low orbit up to a higher orbit. And I'll talk about that more later. The other basic technique is if that long tether structure contains conducting wire in it, you can drive currents along that wire. And those currents will interact with the Earth's magnetic field through the Lorentz force and create forces that push on that whole wire. And you can use that to raise and lower and otherwise change the orbit of a spacecraft without burning up propellant. So basically, tethers have a couple different ways you can use the space environment to provide propulsion without using up propellant. So the way we got started as a company is these long, thin structures in space will get cut fairly quickly by the space debris and micrometeorites that are zinging around in orbit. So back when I was in grad school here, excuse me, I came up with an idea for, instead of just making a single rope, you braid kind of a lace or net structure that can spread apart so you can get pieces cut here and there, but you'll still have multiple redundant load-bearing paths that can enable the structure to survive for very long periods on orbit. So we've done several projects where we've figured out how to design those space tether structures and how to fabricate them. And this is a picture of our 3D braiding machine. It's the only one of its kind in the States that I know of. It's normally used for making things like lacy edgings for kimonos and Victoria's Secret type stuff, but we're using it for making space tethers. So by using the momentum exchange and electrodynamic propulsion capabilities of tethers, there are a number of different missions that you can do that tethers can enable you to do with lower cost than using rockets or other conventional techniques. One is you can use electrodynamic tethers for raising or lowering or changing the plane of a satellite's orbit. And because you're not burning up fuel, you can do continuous maneuvering, constantly changing the orbit of a spacecraft, which you really can't afford to do with conventional propulsion technologies. You can, again, use the tether as a sling to enable one big spacecraft to pick up a satellite or other payload from a low orbit or even a suborbital trajectory and toss it up to a higher orbit. You can also use tethers to grab and drag space debris down out of orbit, and that's been a focus of a lot of the work we've been doing over the past few years. You can also use tethers for tying multiple sensors together over long distances so they can fly together in orbit and collect scientific data like things like ionospheric density or plasma wave characteristics as well as do long baseline sensing, things like interferometry with applications like searches for extrasolar planets. In addition, you can use electrodynamic propulsion to maintain the orbit of large spacecraft over long periods of time. And we in NASA have done a number of studies that have shown that we could save the space station program billions of dollars if they used a electrodynamic tether to do drag makeup on the space station instead of paying the Russian space agency about half a billion dollars a year to launch propellant up to the space station. So tethers are not an entirely new idea. We didn't invent them. There have actually been a number of space tether experiments that have flown over the past several decades. And this is kind of an eye chart, but this is a list of the roughly 20 or so space tether missions that have flown to date. And it's, I don't know if you can really make it out here, but it's color-coded. The pinkish ones did not meet all of their mission, let's see if this works, yeah, mission goals, but the greenish colored ones did meet all of their mission goals. And the important point I want to make here is that over 70% of the space tether missions that have flown to date have been completely successful. That unfortunately is not a commonly perceived fact, because the two missions that most people have heard about, the TSS-1 and TSS-1R missions, they were big, expensive missions conducted on the space station, and both times they had problems because they didn't do the engineering correctly. So unfortunately, NASA upper management has gotten kind of a pessimistic view of how tethers work, and whenever we propose tethers for missions, they say, oh, tethers never work. But the fact is, over 70% of the missions have been completely successful. And one thing I like to point out is, these are the first 20 tether missions that have flown. If you look at the first 20 or so rocket missions that have flown, 80% of those blew up or crashed. So early on in the development of a technology, especially one of a space technology where doing anything right is hard, you got to expect that there will be a number of failures early on before you figure out how to do it correctly. And to give you a little bit more background on some of the space tether missions that have flown to date, the most successful ones were built on what's called the SEDS, or Small Expendable Deployer System platform, so the SEDS-1 and SEDS-2 missions, where they deployed 20-kilometer long, thin, non-conducting tethers down below a Delta II upper stages. In one of the cases, they deployed a payload at the end of the tether and then cut the tether away, and that was enough to drop that payload into a reentry trajectory. And the second time, they deployed it and showed that they could deploy it in a nice controlled state and left it out there for a while to see how long it would last in the space environment. The PMG, or Plasma Motor Generator experiment, also used the same basic platform, but that one deployed a half-kilometer long conducting wire between two small spacecraft, and they showed that you could collect current from the space environment and flow current up and down the tether so that you can do electrodynamic propulsion. Unfortunately, that was a very short-lived and not very well instrumented experiment, so they weren't able to measure the thrust that they generated, but they were able to show that you can flow current both up and down the tether to do electrodynamic interactions with the Earth's magnetic field. But then, as I mentioned, the two tethered satellite systems, or TSS missions, that flew on the space shuttle, both times they had big high publicity failures with those. And what happened with that was, the first time they flew it, about 2 weeks before launch, or a few weeks before launch, the NASA safety and mission assurance people decided that they needed to add an extra bracket to some structure in the tether deployer. And when they reviewed that change, they didn't review it against updated schematics or drawings. And so they missed a problem where there was a bolt that was a little bit too long. But they went ahead and added that bolt and bracket, And once it got on orbit, that bolt jammed against a structure and caused the whole deployer to jam, so they couldn't get the whole tether deployed. The second time they flew it, they brought it back down, stuck it in a warehouse for about 3 or 4 years, and then flew it again without inspecting the tether. And that time, they got rid of the bracket and the bolt. They were able to get the tether almost completely deployed. They got 19.9 kilometers deployed, but at that point, there was a high voltage on that tether, and an arc jumped from the tether to the deployment boom, and there was like 4 kilowatts of power being dissipated in that arc, and that cut through the tether and separated it so that the end mass and the tether floated away from the shuttle. When they brought the remaining tether back down and inspected it, they found that there were little shards of metal that were embedded in the insulator of the tether. And what happened is when they made that tether, we didn't make it, it was made by another company, they didn't make it in a clean environment like you normally do to make space hardware. They made it in just a regular industrial manufacturing environment. And there was dirt and metal shards that got into the tether, and that allowed the arc to jump through the tether. So both of those missions failed not because of the underlying physics didn't work. They failed because the proper procedures and processes were not followed for engineering processes. So even though a tether can sound simple, it's just a wire, just a cable, even though it sounds simple, like any other space hardware, doing space missions is hard. You got to do it perfect or it doesn't work. So, that's the basic takeaway from this is, you got to engineer it properly for it to work. So wanted to get into a little bit of the basic physics behind how space tethers work. So if you've got 2 satellites in orbit around the Earth and they're not tied together, they're just free floating, the one that is closer to the Earth is going to feel a stronger gravitational pull from the Earth than the one that's higher up. Additionally, the one that's oh, never mind. So what happens is that lower object will naturally want to orbit faster than the higher object. So if you put 2 objects vertically separated in orbit, the one that's lower down will want to run ahead of the one that's higher up. Now, instead, if you tie those 2 objects together with a tether, that forces them to orbit together. And they will orbit together at the orbital velocity of the center of gravity of the system. But because the lower object is feeling stronger gravitational force than the higher object, that results in the gravity is trying to pull those objects apart, so that will tension the tether and pull it taut. And then if the system is disturbed away from the vertical orientation, the differences in the gravitational forces and the centrifugal accelerations on the system will provide a torque that will tend to push it back towards local vertical. So a tether behaves very similar to a pendulum on Earth, where if you disturb it away from vertical, it's going to want to swing back and forth. But in orbit, that gets very complicated because the periods of the oscillations in the plane of the orbit and out of the plane of the orbit are different. So if it's disturbed away from vertical, it swings around in weird, complex, chaotic oscillations. Another factor to keep in mind is that a long tether, even if you made that tether out of a steel beam, if it's kilometers long, it's still going to have significant flexibility. And most of the tether materials we use are basically just string, so it has no stiffness along its length. So if you get these forces, electrodynamic or other forces pushing on the tether, it can cause the tether to bow like a skip rope, and there's a whole variety of complex oscillations that can develop in a tether system unless you control it very carefully. So the way electrodynamic tethers work, again, is that we deploy this conducting wire in the Earth's magnetic field, or in orbit, and that system is moving at orbital velocity, 7 to 8 kilometers a second, across the Earth's magnetic field. In this case, the Earth's magnetic field is coming out of the board. So this wire is cutting across the lines of the Earth's magnetic field. And that will generate a Lorentz motion-induced electric field oriented up the tether. And then if you have a means for making electrical contact with the space environment, in particular the conducting plasma that is in the Earth's ionosphere, the system can collect electrons from one end of the tether, and then those electrons can run down the tether and be emitted from the bottom of the tether. And if you do that, if you allow the motion-induced electric field to push electrons down the tether so that you have current flowing up the tether, that results in a J cross B or Lorentz force that pushes the tether back. It opposes the orbital motion of the system. So that's a drag on the system. And what's happening there is the system is basically converting the orbital energy of the satellites and the tether into electrical power. And you can use that to provide power to a payload and lower the orbit of the system. So that's one of the things one of the phenomena that we're working to take advantage of in order to provide a low-cost way of dragging space debris down out of orbit. And I'll talk about that more later. Now, if instead you want to raise the orbit of the system, you can put a power supply in series with the tether and to oppose the motion-induced electric field and pull current down the tether. And that will induce a Lorentz force that pushes on the tether in its orbit and will boost it to a higher orbit. So in these cases, in both of these cases, you're generating a force on the system, but you're not generating that by expelling a propellant like a rocket does. So you might be wondering, how does that conserve momentum in the system? And the way it conserves momentum is the electrodynamic tether is actually using the mass of the Earth as its reaction mass to push against, coupled through the magnetic field. So in fact, momentum is conserved in the system, but you're doing that through interactions with the Earth. And let's see, if you want to hear some of the equations involved in it, the motion of the tether wire across the magnetic field of length L across the magnetic field B, and V is your orbital velocity, that produces that results in the voltage along the tether. And then if you've got current J flowing along that tether, that produces a Lorentz force on the tether system equal to J cross B times the length of the system. So as I said, one of the ways we're trying to use electrodynamic tether propulsion or phenomena is to provide a way to drag space debris down out of orbit. As you may have heard, the Earth orbit is getting cluttered with old satellites and pieces of rockets that have just been left up there and will stay up there for hundreds of years, colliding and making more debris. We've been working for about 14, 15 years to develop a cost-effective way of dragging satellites down out of orbit at the end of their operational lifetimes. We've gone through several iterations of products. We developed several products that basically we didn't sell. They were kind of failures. But we've finally now gotten to a system that I think is really simple and lightweight and low cost enough where we've actually been able to start selling some of them. And that's called the Terminator tape. And it's a very simple system. It's basically just a little box with some folded up conducting tape in it and some mechanisms to enable it to deploy. And the way you use it is you stick it on the side of your spacecraft before it's launched, and then after the spacecraft has finished its mission, you give the Terminator tape device a little bit of current, and that releases the lid on the box, and that gets kicked away by some springs, pulling this conducting tape out. And that tape, this is a picture of tests we did on a Vomit Comet 0G aircraft to show that we could deploy it reliably. This is a picture of a very small unit. It's about the size of a drink coaster that we developed for CubeSats, which are little tiny spacecraft that have become very popular lately. So that tape deploys out, and it both provides a lot of just area to drag against the thin atmosphere that's up in orbit. And it also collects current and flows it along the tape to generate drag forces that will drag a satellite down out of orbit. And the reason, one of the reasons you'd want to do that is that if you were to, the standard way of getting a spacecraft down out of orbit at the end of its mission is basically to reserve a portion of its fuel to do that deorbit burn at the end of its mission. But in order to do that, you have to reserve a fairly large amount of fuel, somewhere 5 to 20% of the spacecraft's mass, in order to drag it down out of fuel, and that translates into shorter operational lifetime for the spacecraft. In addition, to use a rocket to drop it down out of orbit, you got to be able to point the rocket in the right direction after the mission of the spacecraft is ended, and a lot of times that's not the case. Things on the spacecraft fail, the power system, the momentum wheels, other components, and you're not going to be able to point it. So the solution we've got is we just pop this tape off, and the gravity gradient pulls it out and orients it in the right direction, and it comes down on its own. And these are graphs of the mass, the mass fraction you would need of propellant for a spacecraft as you go up in orbit for rocket systems. And with a tether system, you can do the job with much lower mass impact on your spacecraft. So these are some more pictures. We've done several 0G experiments on the 0G aircraft, deploying various tethers and tapes. And here's some pictures of the deployments we did. So we've shown that we can deploy it successfully in microgravity, and our first unit that we've sold is due to be launched later in the fall. So hopefully within about a year, we will have a flight demonstration that this crazy idea works. So looking at bigger and more capable systems, one of the other systems we've worked on with NASA is using electrodynamic tethers for moving spacecraft around in orbit. And we recently completed a project called Propel, where we were working on a design for a electrodynamic propulsion system for microsatellites, satellites around 500 kilograms in mass. So the red lines are meant to illustrate the magnetic lines of the Earth's magnetic field. They're in a dipole shape, and if you're in an orbit around the Earth, you kind of circle around the Earth, and what happens is because the relative angle between the magnetic field and the tether is changing constantly as you go around the orbit, you can end up getting electrodynamic propulsion forces that can either raise or lower the orbit of the tether system, but you also get forces that can push it from side to side. And if you control it properly, you can actually change the inclination of a tether system orbit, which using conventional technologies is extremely expensive. Tethers are basically one of the only ways of affordably changing the inclination of a spacecraft's orbit. And because a tether system is not expelling propellant in order to push a spacecraft, it can enable a spacecraft to escape the limitations of the rocket equation. When you use a rocket equation, there's an equation that describes how much of your system mass you need to burn up in order to get a certain change in velocity of the system. And if you look at electric propulsion systems like Hall thrusters, which are very popular right now, resistojets, which heat up a gas using electricity, they're all kind of limited below this line in terms of the thrust to power they can generate and the specific impulse. Specific impulse is kind of the measure of fuel economy of the system, how much propellant you need to burn up to get a certain change in the velocity of the system. But a tether system, because it's using the space environment to move stuff around in orbit, it can provide both very high thrust levels and very high specific impulse. So a lot of torque out of your engine and a lot of fuel economy. And what that ends up meaning is that tethers can enable you to do missions that require very large delta Vs, very large total changes in the velocity of the system. Things like constantly moving around to different orbits to reposition a Earth-observing telescope, or constantly thrusting to keep a space station up in orbit. So that kind of wraps up electrodynamic propulsion. The other main use for space tethers is momentum exchange propulsion. That's where you're using a tether to sling an object up to a higher orbit. And right now, we're working under a project funded by NASA's Innovative Advanced Concepts program, which is kind of a small part of NASA that funds kind of crazy far out stuff, on a project called, to do a project called NanoThor. And let's see what's going on here. Sorry, I seem to be frozen up. Okay. So the idea on NanoThor is we're trying to come up with the smallest, simplest tether system that can, a momentum exchange tether system that can do something useful, basically. And the idea here is that if you want to launch a very small spacecraft out into deep space, say send it to the moon or send it out way past Earth's orbit to look at asteroids or other missions, right now there are a number of people or organizations working on very small spacecraft, things like CubeSats, which are about the size of a loaf of bread, and nanosats, which might be the size of a microwave oven. And a lot of them would like to do missions out in deep space, go to the moon or asteroids or whatever. But right now it's almost impossible to find a ride to get out there, because either you have to buy your own rocket to get out there, which is extremely expensive, $50 million or more, or you have to hitch a ride on another launch. But launches to deep space destinations are very, very rare, maybe at best one a year. So what we're trying to do is provide an affordable and frequent opportunity to get these very small spacecraft out to deep space destinations, so we can lower the cost of doing exploration missions. So the idea here is your nanosat and our tether module would launch as secondary payloads on launches of geostationary satellites, like communication satellites. And so they'd ride as a secondary payload on the upper stage, and after the upper stage has released the communication satellite off to do its mission, then we deploy the nanosat at the end of a tether. It'll be a fairly long tether. It looks like it'll take about a 30-kilometer long tether to do this, which is pretty long. So we'll deploy it down, deploy the nanosat at the end of the tether, and then we'll use a trick where we use the gravity gradient field of the Earth. We deploy it down and use the gravity gradient field of the Earth to pull it and get it spinning a little bit. So we got that 30-kilometer long tether spinning a little bit, and then we just start reeling the tether in shorter and shorter. And like the ice skater pulling her arms in, speeding up, the tether system will start spinning faster and faster until we can actually get the roughly 800 meters per second of velocity for that nanosat that the system would need to toss it to Earth escape. So we could toss it out past the moon or off to an asteroid. And then could actually do it over and over again, put an additional nanosat at the end of the tether, do some more trickery to get it spinning, and toss more satellites. So this is one of the projects we're working on right now, and it actually looks like it'll take a very, very reasonable and low-cost set of hardware to do this mission. so as I said, we need to deploy. This is a graph of kind of the program that I developed for doing this. Over the period of two orbits in geostationary transfer orbit, which is a highly elliptical orbit that comes in very close to the Earth and goes way out near the geostationary satellites. So over the course of 2 orbits, we would deploy a little over 30 kilometers of tether. And then over the course of 3 more orbits, we'd pull the tether back in, spin it up until we can toss the payload. So basically, we can just use simple reeling of a tether in the Earth's gravitational field to get a lot of velocity into a satellite in order to get it off to deep space. Now, we've also done a lot of work looking at bigger systems, much more science fiction-y systems, where we'd use something like a 100-kilometer long tether in orbit around the Earth that would dip down to low Earth orbit and pick up payloads from either suborbital trajectories or low holding orbits, and then toss them out to geostationary orbit or to the moon or whatever. But when a momentum exchange tether picks up and tosses a payload, it gives some of its orbital energy and momentum to the payload. So the tether system's orbit will actually drop. And for the system to make sense economically, you need it to be able to boost many payloads. So you need a way to restore the orbit of the tether system. And the way you can do that is to use electrodynamic propulsion, so that every time the tether swings down close to the Earth, you drive current through the tether and boost its orbit back up. So if we can get to being able to deploy a big, long tether system like that, it could service multiple markets, like sending satellites to geostationary orbit, send payloads out to the moon to supply a lunar base, and support interplanetary missions. Now, so that's some of the space tether work that we've been doing, but we've also done a lot of work trying to find applications where we can take the technologies we've been developing for these kind of far out space applications and apply them to terrestrial applications here on Earth. And one case is we did a project with NASA where we were looking at having a system that could shoot a tethered sensor out from a planetary lander, on Mars or the moon or whatever, to do science there. So we developed a technology for being able to shoot out sensors with a tether attached to them. And then we were able to transition that technology to one where we've developed systems for deploying optical fibers, both for submarine communication buoys as well as mobile robots. Another project, in another NASA project, we developed some hardware, a winch system for deploying these very high-strength, high-load tethers in space. And recently we used that winch technology to enable us to make a very small system for deploying and towing sensors behind unmanned aerial vehicles for mainly for a Navy anti-submarine warfare application. In addition, a few years ago, we did our own space mission where we launched 3 tiny little CubeSats with a tether attached between them, and had hardware to inspect the tether on orbit. And we're also able to transition that to a technology where we can have a system that will crawl along the guy wires, the big cables that hold up that stabilize a communications antenna. We developed a system that can crawl along those wires and inspect them to detect corrosion and other defects in them. So let's see. So that kind of covers the tether stuff that we've done, but I wanted to mention some of the other cool technologies that we've been developing at Tethers as we branched out into other areas. One of the one of the most exciting fields in the space industry right now is CubeSat and nanosat technology. Very small, low-cost missions, low-cost systems that can enable you to do missions with much smaller budgets than previously required. And earlier this year, we finished up a project where we developed a high-power deployable solar array for these tiny little spacecraft. Spacecraft about the size of a loaf of bread can unfold this pretty big solar array and generate up to 80 watts of power, which is quite a lot for a small satellite system. And then we're working to combine that high-power deployable array with a new thruster technology that uses electrolysis of water to produce hydrogen and oxygen for a rocket system. And the idea there is you could launch your CubeSat filled up basically with just water. So it's got no stored energy, it's inert, it's a green propellant, and then process it on orbit into the fuel and oxygen you need to provide thrust to one of these small CubeSat systems. So that's a project we have going on right now, and we've shown that we can get a fuel cell working in tandem with a thruster to give us pretty good thrust levels for a small spacecraft. Another project that we've been working on is a very small, compact, but high dexterity robotic arm to enable these nanosats and CubeSats to perform missions like on-orbit servicing, missions like unsticking a stuck solar panel on a bigger spacecraft, as well as on-orbit assembly of space systems. And we just recently delivered the first prototype hardware to the Naval Research Lab, where they're going to be using it to develop new techniques for controlling robotic arms. Another area that we've been doing a lot of work on recently is the use of 3D printing and other additive manufacturing technologies to fabricate multifunctional spacecraft structures, both here on Earth and out in orbit. One project we've been working on is we're developing a way to use 3D printing to fabricate spacecraft structures that have radiation shielding embedded within them. And it uses a technique called graded Z shielding, where you have layers of materials with different atomic weights, and if you layer those materials properly, you can shield out the space radiation with much lower mass required than it would take if you use conventional shielding techniques, like just putting more aluminum in the structure. And then the other area we've been working on is figuring out how to build big systems on orbit, particularly to fabricate them on orbit, not just carry up the parts, but carry up raw material and process them on orbit to make very large structures, like huge, football field size antennas and very long trusses. So we're doing a lot of work kind of adapting 3D printing and composite layup techniques to enable us to make things like trusses and antennas and other structures on orbit. That project is called SpiderFab, and that's also funded by NASA's Innovative Advanced Concepts program. So to kind of wrap up, space tethers can provide propulsion to spacecraft without consuming propellant by interacting with the Earth's the space environment itself. And what that can do is it can enable you to do missions that require very large total delta V, very large total changes in the velocity of the system, and do it with very low mass requirements. The electrodynamic tethers generate thrust and can do it with very good fuel economy and pretty good thrust levels, and do it by interacting with the Earth's magnetic field. And momentum exchange tethers basically acts like a long sling to transfer energy and momentum from one object to another. And one of the big things I was hoping you'd take away with is that, although the common perception is that tethers don't work, in fact, most of the tether missions have worked. It's just, like any other space technology, it's very challenging, and you've got to do the engineering carefully and properly in order for it to work. So, in general, tethers are still they're a high-risk technology, and NASA and the space industry are very adverse to risk. But if we can figure out how to get these systems built and operating correctly, they can provide very high payoffs, enabling you to do a lot more science, provide a lot more mission capability for much less funding. So I'll wrap up there and take any questions you have. Thanks very much.
Then I'll ask the speaker a question. You mentioned one of the types of technologies that you're selling. Could you comment on how much of what you do, how much of the work you do is commercial, and how much you sell commercially, and how much of the work is funded and sold to the government instead?
Pretty much all of our funding originates from the government in one way or another, either directly from the government in these research and development contracts, or where we're selling products, it's typically to a bigger company that's building a satellite system for the government. So, at this point, over 95% of our business originates somehow with the government. We're working hard at bringing out these products and have started to make inroads into the commercial sector, but we're working on that. But it's still mainly government R&D. Yeah.
How cost efficient would a tether system be in comparison to a comparable rocket system for doing the same cost?
Well, as an example, we'll take the deorbit system. The Terminator tape. A rocket system to do the same job would require not only somewhere between 5 and 20% of the mass of the spacecraft, but that rocket system and all its engineering impacts could say be several millions of dollars impact to the satellite program, whereas we're now selling a product that's $50,000. Which is, sounds like a lot of money, but in the space industry, that's basically free. So it's still an uphill battle for us to sell that technology because it's a new unconventional technology. As I said, the space industry is very risk adverse, but we are starting to make inroads there. Yeah.
How long will it take your Terminator tape to deorbit a satellite?
It can take 5 to 10 to 15 years. It takes a while. It depends upon how high up the satellite starts. But basically what we're trying to do is provide an affordable way for satellite users to comply with new requirements to bring their satellite down within 25 years of the end of their mission. So right now, until recently, companies and organizations just left the satellite up there and they'll stay up there for hundreds or thousands of years. Now the government and other organizations are starting to require people to bring them down in 25 years. So what we focused on is enabling them to just meet that requirement with the minimum of cost and mass. We have other techniques where you could bring it down a lot faster, but they cost more. So there's a trade-off there. Yep.
You notice most of the tethers were actually meshes to increase the lifespan of them. How much more could that increase the lifespan, I guess, significantly over time compared to a larger tether before?
It's not necessarily a larger tether. It's just a single braid like a shoelace. Well, as an example, the SEDS-2 mission, where they deployed a 20-kilometer long tether that was about the size of a shoelace on orbit, that was cut within 4 days. So it separated within just 4 days. But if we took the same amount of material and kind of spread it out in this fine lacy mesh, that could last many years on orbit before it finally separates.
Well, thank you.
Okay, thanks.